Okay, so back to modeling the thermal responses of traits. All right, so like I said earlier, I pointed out that I made a typo. All right, the first one is lost. All right, so the equation, like I have said, is just coming from the schematic diagram, and I think I've been able to explain to us that each of these development rates are temperature dependent. This lambda A actually is the force of infection, and this force of infection actually includes the biting rates, and the biting rate itself is also temperature dependent. All right, so let's move forward. So now, um, let us not be perturbed by what we are seeing on the board. They are simple things. I'm not going to spend so much time here. We are still going to see how some of these things can be done in the other slides. But let me just quickly explain just one or two things in this place. So the table below provides the traits and their temperature dependent functions for the previous equation, which is this. In this particular situation, we are looking at the stages. We are looking at the egg stage, the larva stage, the pupa stage, and then the adult stage also. So each of these rates, as I've told us, they are temperature dependent. And so what we have here now is that particular temperature dependent function that corresponds to each of the traits. So what we have on the first column is the temperature dependent traits, and then what we have on the second column is their corresponding temperature dependent function. Please, are we together? Yeah. Now, one thing is, let us just follow. When we get to the next model, all right, we'll see this more clearly. Yeah, we'll see this clearly. But let me just quickly say here that you will notice that we have one is just ordinary T, then we have other ones, T subscript W. That's talking about the the normal T is just the air temperature, while the other T subscript W is the water temperature. Because one, you are looking at the aquatic stage of the mosquito, so you want to factor in the temperature of the water. Are we together? And studies have found out that there are authors who have come to find out that the water temperature is only 1 or 2 degrees higher than the air temperature. All right? So meaning that even though you may not have the water temperature, if you have the air temperature, all right, the only thing you just need to do is that you have the water temperature, okay, equals to the air temperature. We can have it as maybe T subscript A, meaning air temperature plus 2. All right? So because sometimes you may not really have access to the water temperature. Okay? So maybe the media could help us check this as other people can also see it. So the water temperature is just 2 degrees, 1 or 2 degrees more than the air temperature. But some authors made use of just TA plus 2 as the water temperature. In fact, there are some possibly papers that you will find out that when they want to give the function, please to the slide now, when they want to give the function, maybe instead of writing T subscript W, they just put T plus 2, telling you that the air temperature plus the 2 to make up for the water temperature. Please, are we together now? All right, so, and these functions are actually based on the laboratory work of Maharaj in 2003. But please, caution has to be taken. And please, we have to take note of this. Caution has to be taken on the way we use some of these functions. Even the one you are going to maybe fit yourself because you have access to the data. Caution also still have to be taken. Reason being that, let's take for instance, maybe you are looking at a particular trait of the mosquito. I'm taking pain to explain all of this because there will be a time that we have to run so fast on the basis that you understand now what I'm saying. That's why I'm taking it slowly now, all right? Okay, so, although not so fast too. So we have, let's say, some temperature values. We have 20 degree, 25 degrees, let's say 27, and let me just say 29 degree. No, let's just for instance, all right? And let's say you have a particular trait that you are trying to consider. You want to see the relationship between that trait and temperature, for instance. But if you look at this very well, we only have data for 20, 25, 27, and 29. But in your local environment, or the local location, the local geographical location you are considering, well, the data you have something like maybe 24, 26, 28, 30, 31, 32, 33, 34, even in some cases like Zamfara, the northern states. Are you getting it now? But the data you have do not capture for all of those. So now what you want to do is that now you want to come up with a function, all right, to capture that particular trait as a response to temperature. So the first thing you need to do after you have done all of that, which you are still going to see, is very, very important for you to plot it out using that various temperature values to see if the result is actually sensible. Because there are times when you do that, maybe you want to use that data to generalize what the behavior may be. Sometimes you may run into having negative traits. And you know, for instance now, if mosquito biting rate is -2, biologically, does it make sense? No. Are you getting it now? So sometimes you want to take caution in that aspect. That is why for some of these functions, before you make use of them, you may first want to check their plots. Your plots, let's see how it looks like. And based on what you see, sometimes you even want to restrict them. And sometimes you even want to also further understand the biology of that trait to know if actually what you are coming up is biologically sensible. Please, are we together? These are very, very critical issues when it comes to using some of these functions. Because I remember when I was trying to run some of these functions, for some of them, they only have good values from 31 to 35. Just from 31 to 35. I think the development rate, which is this. If you try out these functions, I think it only gives you good values from 31 degrees to 35 degrees. So many, if you have 26, 27, all of that, you run into negative. So sometimes care has to be taken. And I also have to state here that these functions were actually based on laboratory studies done by this Maharaj, and they were on Anopheles harambiensis. It's a species of Anopheles mosquito. But majorly in Nigeria, we have the Anopheles gambier, Anopheles funestus. Please, are we together? So sometimes the function you want to use, you want to understand the data used to generate that function. Are you getting it now? Although there are also times that the response you want to capture, data is not available for it for the particular species of mosquito you are trying to capture. Sometimes as a proxy, you want to use another species of mosquito to be able to do that. And that is why it's very, very important. Whenever you are coming up with your modeling work, some of the limitations, some of the things you have done, is always better you spell them out in your manuscripts or in your discussion with the policymakers so that they also can see the need to get entomological data in order to be able to make good decisions. As we have been told by Prof and my other colleagues, we know that the quality of the results you'll be bringing out from your modeling work is largely dependent on the quality of the data too. Please, are we together? Very, very important. Now, let's go on. So, incorporating these functions into our models, not those ones, we are still going to see the ones we are going to incorporate. Using the base malaria model introduced in the previous classes by Dr. Afis. Do you still remember? All right. All right. So using the base malaria model introduced in the previous classes, the description of the vector dynamics is provided here. Let's call the malaria model again. So this is the malaria model, and this part here where we have the SM, EM, IM, is the mosquito population dynamics parts. Are we there? And then we want to see what we have here as the lambda hem. The lambda hem we are seeing here. Thank you, the media. I really appreciate that. The lambda hem we are seeing here is talking about the recruitment rate by birds into the susceptible class. All right? And some authors make that to be constant. They just give it a constant value to it per time. Maybe let's say 2,000 per day. For instance, some authors just give a constant value for it. This one is talking about what comes into the adult susceptible class. Are you getting it now? But now, in the real sense, you know, one of the things why we engage in modeling exercise or modeling work is the fact that you also want to predict, to know how the disease dynamics will be. This is 2025. Sometimes you are interested in knowing what the disease dynamics will be in 2026, for instance. But there are factors that influence even the observed data that you have now. And now, to make those predictions, you want to incorporate those factors influencing the observed data that you have now to be able to make at least something reasonable, something more realistic. Are you getting it now? So making use of constant recruitment rate may not be the best option. So the next thing you want to think, therefore, is how do I deal with this? Not neglecting what is coming from the immature mosquito. Please, are we together? So now, as I've said, a modeler have his or her interest. Are you getting it now? And they have the ways they want to go on to carrying out whatever it is that they want to do. Some will go to the extent of, if you look at this now, we have about 1, 2, 3, 4, 5, 6, 7, 8 compartments, isn't it? Some modelers, the previous model we look at, where we have the egg, the larva, all of those, the the 3 stages, which is egg, the larva, and the pupa, they want to also bring it in. Are you getting it now? But the qualitative analysis of that may not be so easy. So you also want to look at how you can simplify some of these things. If the immature is not actually your major interest, are you getting it now? And yet you still want to make out something realistic with it soon. Okay? So, these are just the causes of infection. The model is associated with digital condition. So now, seasonality is one of the variations observed in malaria, that is malaria data. These seasonal variations are influenced by human activities, climate variables, etc. Several authors have introduced seasonal forces to capture seasonality observed in malaria data, but this has limitations on prediction, as the sources of variations cannot be captured by just time-dependent functions alone in order to forecast or predict future malaria risk. By saying time-dependent function alone, Prof told us about seasonality, systematic peaks that is observed, maybe for instance in malaria cases, maybe per year. Are you getting it now? That is seasonality. And now, to capture, because your model actually, what you are using your model to do is that you want to, actually, this is deterministic model, also called process-based model. You want to explain the process or processes that produce the data that you have with you. Are you getting it now? And that you have integrated into the model. So, and now that you know that, oh, there is seasonality and all of that, you want to ask that what are some of these things, what are some of the things that can follow these seasonal patterns? One, the biting rate can follow that seasonal pattern. Are you getting it now? The abundance of mosquitoes can follow that seasonal pattern. Are we together? And so you want to look at those two entities to capture the seasonality. For instance, now we have the biting rates, which is just a constant value. But because you want to capture seasonality, sometimes you want to introduce a seasonal function, what we call seasonally forced function, something like 1 plus a sine 2 pi t over p plus maybe a phase angle, for instance. Are you getting it now? Now, please pay attention. I have reasons why I'm explaining this. If you plot this, all right, This one only give you value that ranges from um, between 0 and 1. So now, if you plot this, no, that is slightly more than 1. If you plot this now, you are going to have something that looks like this. Something that looks like, for instance, something that looks like. Are you getting it now? And it continues like that. So now you are saying that your biting rate follows this sinusoidal pattern. Are you getting it now? But in the actual sense, that is not the case. But because you want to capture that seasonality, you make it go this way. It's just an assumption. Are you getting it now? But now that you want to now bring in climate variables, all right, you want to look at the local, for example, you're looking at, let's say we're looking at Benue State. You want to look at the local climate variables. Are you getting it now? And how they influence the biting rates. You want to include it in your work to make your model more realistic. Are you getting it now? So that is the essence of what we want to do. Please, let's go back to the slide. So several authors, okay, but this, okay, I've talked about this. So some of the mosquito-related parameters of the model are temperature dependent, as we have seen. So there are two types of functions that are being used to model the temperature-dependent parameter, namely the Brière function, which is this function we are seeing here. The T mean represents minimum. These are critical temperature values. This one represents the minimum temperature. This one represents the maximum temperature. That is the minimum temperature where that particular trait can survive, and the maximum temperature where it can survive. Are we getting it now? That's what these two are talking about. Then this represents the other temperature values. Then the second one that is also used to model the temperature-dependent parameters is also the quadratic functional form, which is this. We all know quadratic, right? And these two functions, they are unimodal functions. What do I mean by saying unimodal? As I've said earlier, they look like this. Are you getting it now? Reason being that this model the biological traits, the thermal response of those biological traits. Please, are we together? Please, are we together? All right. These functions are unimodal, as I've said, corresponding to field observations of the thermal responses of biological traits associated with the female Anopheles mosquitoes. Therefore, for our model, it is important to highlight some of the temperature-dependent parameters in our model. So, at this point, I want us to be more together. We've been together, but this time, more together. All right? Okay, before I go on. So, who can give us maybe two of the biological traits associated with the that we can find in the mosquito dynamics that are temperature dependent? Just two. The biting rate, the parasite development rate. Do you see about that ones? Egg deposition and all of that. Okay, thank you. So they are the maturation rate of immature mosquitoes into the adult mosquitoes, which is a function of the temperature-dependent number of eggs laid by the mosquito. We are still going to see this mathematically. The temperature development rate of the eggs to adult mosquitoes, and the probability of survival from the egg stage to the adult stage. So let's look at each of these one after the other. All right, so now let's pay attention. The first thing we want to do is that constant recruitment rate by birds, okay? We want to make it temperature dependent. Are we there now? So that is where you want to introduce your climate variable, which is temperature. For now, I will only be talking about temperature. Are we together? All right. So this was constant before, just lambda m. But we're not saying that this actually can also be defined as this. This is just talking about the birth rates of the adult mosquitoes. And if you look at what we have here now, a lot of things have been lumped together. Do we see it that way? Though I'm still going to explain each of the terms, but a lot of things have been lumped together here. Here, we're not talking about egg, larva, pupa. Are we there now? Because in this base model that we are using, all right, we are not actually interested in those parts. Are you getting it now? Not that maybe they are not necessary or important, But as far as we are concerned in this model we are looking at now, we are not interested in that part. Are you getting it now? And yet, we still want to find a way to include our climate variables. So we look at, okay, we can have seasonal variation in this particular part. So how do we introduce that instead of making it constant? So we have in this place the eta E represent the temperature dependent number of eggs laid by the adult female mosquitoes. Are we there? Then the PEA is the probability of survival from egg to adult stage. You will now see that probability of survival from egg to adult stage has lumped a lot of things together. Are you getting it now? Instead of we moving from this to this to this, do you get what I'm saying? So we have just lumped together, okay, if you have the eggs, okay, the probability that it's going to survive to the adult stage, we have incorporated it here into the birth rate of the adult mosquitoes. Are you getting it now? But you also see that even what we are looking at is still starting from the egg, isn't it? All right, then we have the development rates from egg to adult stage, and that happens in time, right? But we have made it now a function of temperature. Then this is the logistic part of it, owing to the fact that we have limited breeding sites. I'm getting it now. The K there represents the carrying capacity, right? I think I remember Prof talking about this in the morning. It represents the carrying capacity. Water is not everywhere. Are you getting it now? And then even the water available sometimes when the mosquito want to lay eggs and find out that other eggs are there, it will have to search for another breeding habitat in order to lay the eggs. And that's why we have the introduction of the logistic. We are making the birth rate to be logistic birth rate. The M is the total number of the adult mosquitoes. The total number of the adult, that is the S, the E, and also the I. That is what that M there represents. So next, we need to obtain the temperature dependent function for each of the identified variables. So this movie actually represents their death rates, because the laying of the mosquito can only lay eggs as far as it's still alive, isn't it? So now what we just have here, the number of eggs is able to lay per time, all over the mortality rate. Are you getting it now? It's giving us the number of eggs it can lay throughout its lifetime. Are you getting it now? That's what that one is just trying to capture. And I think another name for that is what we call fecundity in biology. Fecundity in biology. All right. Next, we need to obtain the temperature dependent function for each of the identified parameters. So, okay. It's okay. Sorry about that. Okay. But can we see this? Don't worry, I'll be making reference. We'll be going back and making reference. So maybe the media, please just help us in any way possible. Okay. So now, we want to look at each of these. What we have here is observed data. Are we there? Are we not seeing this? Okay. Okay. So can I continue? All right. So now, what we have here is an observed data, studying the relationship between the trait of the mosquito and the temperature. Now, the assumption here, all of these do not, they are not just there also without some assumption. We know that, like what Prof said yesterday, let's listen to this. Prof said something yesterday very important, and that's has a lot of things to do when we are talking about climate variability. Remember, he said he was in a particular country. He went out in the morning to get something, isn't it? And he has not walked up to 30 minutes. What happened? The weather changed. Are you getting it now? The weather changed. He had to run back to his home and to his house to cover himself. Are you getting it now? That is to tell you how temperature can change even within a day. Are you getting it now? But the assumption here now is that the temperature is constant. Are you getting it now? Reason being that you cannot capture all those variabilities. Do you get what I'm saying now? So that is why Prof said something yesterday that all models are wrong. Are you getting it now? Because there are a lot of assumptions. But does that mean they are not still helpful? Actually, they are helpful. Are we together now? All right. So now, one of the things you want to do is you want to look at the relationship between this and this. And I have showed us earlier the functions that can be used to actually capture this. You make use of these, or you make use of this quadratic functional form. There are some of the biological traits that the quadratic form fits better, and there are some of them that the Brière function fits better. Are we getting it now? I cannot really go deep into the mathematics of that now, so let's just take it that way. Okay, so now what you have here is I use the quadratic function, okay, to fit a curve to this data. From the legend you can see here, you can see this point here represents the original data. Very critical. That's the original data. Are we there? And this, what we have here now is the temperature values. So we fit this quadratic curve to this data as though to use that equation to represent the relationship between probability of survival from egg to adult, making it temperature dependent. Because if you look at it here now, at least looking at our graph, you will see this one is showing relationship between temperature and proportion, isn't it? Proportion of egg that survive from egg to adult. That is the relationship. So, and if you want to represent that relationship, that means what you want to do now is that you want to say that the proportion, which is dependent on temperature, are you getting it now, is a function depicted with quadratic equation, and that is what you are seeing. That's what you are seeing there, that the PA of T, that is the probability of surviving from egg to adult, a function of temperature, is given as this. So what you are actually seeing here as the function is the red curve that you saw in the previous slide. Please, are we getting what I'm saying? This red line now, we are using it to represent our data. Because we need an equation. The data does not contain all the temperature values that we have. That we need. Are you getting it now? So, but now you have come up with an equation to capture that particular trait, such that you can bring in other temperature values to capture that particular biological trait in the mosquito dynamics. Are you getting it now? Please, are we following? All right? Okay, yeah. Thank you. So this, yes, this curve fitting actually was carried out using what we called, I think Mr. Ido or Mr. Ida, yes, I think we will still be taking through curve fitting. Are you getting it now? So now, and that is why Mr. Ido mentioned something very important the other time. So we are putting all the pieces together. Those statements are not just mere words. All these are pieces. Are you getting it now? And by the time you are doing curve fitting, you should be thinking of, okay, how do I use this in this curve fitting now? Can I also carry this out myself? Are you getting it now? Very important. In fact, you can take it up as an exercise that, okay, having been taught curve fitting, now you have the data, isn't it? Can I bring that data and also fit the curve and see if I'm going to get exactly something like this or something close to this? Are you getting it now? That is why we are here. That is why all these pieces, they are interwoven. Don't neglect any of them. Please, are we together? All right, so I have to move now. So similarly, the development rate of the eggs to adult stage can be fitted using this data below. This data here now is talking about the mosquito development rate, that is from egg to adult. Are you seeing that now? So I can also fit the curve to obtain what I have here. Are you getting it now? Just like what I did in the previous one. Just like what I did in the previous one. Is it still moving like this? Not moving again, no? Okay. Yeah. So just like what I have here, all right, we can do the similar thing to this. How you getting it now? We fit the curve to come up with this equation. The daily adult survival probability is also fitted as this. This one, the data is large, so I can't put it on the slide. Are you getting it now? The data is somewhat large, so I can't put it on the slide. Then it's also given as this, which is also temperature dependent. Then we have the, so if this is survival probability, you know, that is the probability that the egg survive from egg to adult, right? Let's say if it is 0.5, the probability that it does not survive will be 1 minus 0.5, isn't it? So, and that's why we have here, the death probability is therefore 1 minus probability that he survive. Are you getting it now? So that the temperature dependent death rate of adult mosquito is given by this, minus log, all of that, because there's a way you can convert proportion to rates. Are we together? There's a way you can convert proportion to rate. That is given as rate equals to minus ln 1 minus p over the time difference. Okay, please, we can write this down. It's very, very important for us. We may also we may need something like this in our projects too. So it's very important. So, and now that we already have the probability of survivor, but what we are looking at now is death. So that means what we have now will be 1 minus p. By the time you do 1 minus p, you will be left with ordinary p. So that this one now will be r equals to minus ln p. Since it is per day, that's just 1. So we have minus ln p. But we know what our p is already. We know that our p is already that p subscript x equals to all of that. So we just have the death rate, therefore, to be minus log whatever our p is. So it just follows. Okay? So next, let's look at the number of eggs laid per day by the mosquitoes, which is the eta T. So we have egg lays by female mosquitoes per day. At 20 degrees Celsius, this is what it lays. At 25 degrees Celsius, this is what it lays. At 30, 35, this is what it lays. Very short, but that is also fitted to look at that relationship. And we have this particular plot. So now, if you look at what is here, okay, sorry, to get this rather, this is not a plot, to get this particular function, that we are seeing here, please, yeah, to get this particular eta of t, which is talking about the eggs laid by the female mosquito per day, which is also temperature dependent. All right, now, all of these things that we have looked at, let's go back to the birth rate of the adult mosquito that we're looking at. You will see now that we've been able to get this, right? We've been able to get this, isn't it? Which is the death rate, but we have not, okay, it's like we have not touched this. Okay, but let's go on. Oh, let me know, I didn't include it or something. That is the development rate. Okay, we have looked at that. That is the mosquito development rate, right? The MDR, mosquito development rate. We have looked at that, which give us this. So sorry, I didn't put the sigma, the phi there. So now, bringing all these pieces together, the egg laying, the death rate, the probability of survival, the egg development rate, are we there now? With the logistic part of it, and plotting it, give us this particular graph. And now, if you look at this one is talking about the birth rate of the adult mosquitoes. If you look at it, it looks like what I told you earlier, a unimodal function. Are we getting it now? It's not constant. It's telling us now that at specific temperature, are you getting it now? The birth rate is different. You will see that at a specific temperature, it is at its peak, isn't it? And then after that temperature, what begins to happen? It begins to decline. This follows what is observed ecologically. Are you getting it now? This follows. All right. So now let's see the biting rate. Because as I've said, under the force of infection, we also have the biting rate. So this one here is the temperature. This O here represents the time to oviposition. You know, after the mosquito have sucked the blood, fertilized the egg, it moves around to oviposit. Are you getting it now? That is to lay eggs. So the time it takes at 15 degrees Celsius is 12.8 days. The time it takes at 20 degrees Celsius is 6.4. Are we there now? So that can also be used as a proxy to calculate the mosquito biting rate, owing to the fact that, okay, if it takes this time to oviposit, there's the assumption that the mosquitoes still want to come back again to bite. Are you getting it now? To bite, to get blood, to fertilize the egg. Please, are we get what I'm saying? The assumption is that, okay, after oviposition, the mosquito want to return after those number of days, all right, to bite again. So you can use that number of days, the reciprocal of it, 1 over that number of days. We can use it as a proxy to calculate the mosquito biting rate. Are we following now? All right, and that is what this A here represents. All right, if you find 1 over all of these, you are going to have all of this in this place. This data, you can find it in the work of Mordecai et al. Maybe, I don't know, in one way or the other, maybe that will be shared later. So, but how do we capture that? So, we capture that using a quadratic fit. This may look like a straight line, but in the real sense, it's not actually a straight line. It's coming from a quadratic function. Are we getting it now? So, this just happened to be like, almost like the straight part of that quadratic function. Are we together now? All right. So plus showing relationship between temperature and biting rate, and this is the function for the biting rate. So we can now, so to solve that particular model equation, are we there now? Which is our main malaria model equation. We can integrate this now into the model, perform the numerical simulation in order to see our results. So I'm going to like to stop at this junction. Thank you so much for listening.